There you go. What could we call this compound other than alkene? It's got this carbonyl. It's an alpha-beta unsaturated carbonyl. Because from the carbonyl, the first carbon's alpha, the next carbon's beta. The alpha-beta position is unsaturated. And we did that by eliminating this. A two-step sequence. If you're given this and you're asked, how could we put in a double bond right there? You might think, well, I need to remove two H's, put in a double bond. Well, how are you going to remove two H's? We've never seen a reaction to remove two H's. We've seen added two H's. I mean, if we have this, how can we get to that? We could add two H's with like palladium on carbon or something. That's an alkene hydrogenation. Have we ever seen removing two H's? No. But we can do it sort of a roundabout way by alpha halogenating, put it in a leaving group, and then do an elimination, which we well know, make an alkene. By the way, on the quiz, the mechanism did not involve an E2 elimination. What is a requirement for E2 elimination? Sterically hindered, usually, but the base is more important. What type of base? Strong base. Okay, in the mechanism on the quiz, did you have a strong base? We had the amine, which was the reactant, and then we had an acid, paratoluene sulfonic acid. You cannot have strong bases under acidic conditions. You do not do E2 eliminations under acidic conditions. This is all organic 1, right? Instead, we did it more like an E1 elimination. Make cation first, or a resonance structure of a cation. The other thing on the quiz, some of the top reactions, a lot of people did partial reaction and then didn't do the further step. For example, reductive amination, you make imine, and then the imine gets what? Reduced to the amine. That's the purpose of the sodium cyanoborohydride. And I'll make a comment that in studying, I wonder when studying if you don't make connections of what we're doing. We introduced sodium cyanoborohydride, the purpose of it. You know, I know it's you know the first time maybe you've ever seen it, stuff like that. But please, when you're reviewing your notes, look at what we're doing. If you have a new reagent, you should say, well, what is this reagent? What's the purpose of it? And then be prepared to use it. Okay, this is one way to make alpha-beta unsaturated carbonyls, or actually it's a ketone, alpha-beta unsaturated ketone. We'll see another way probably on Monday. The aldol reaction also gives alpha-beta unsaturated ketones. On Monday, by the way, we'll have another quiz on everything we've covered up through today. Test is next Friday, right? Test cannot be moved because the following Monday is the last day of class. It will be next Friday. Okay. Exhaustive deuteration. What's it good for? Just like halogenation, we can exhaustively deuterate. What is deuteration? Well, apparently we're putting deuterium. Just like what is chlorination? Putting chlorine on something, or okay? Where does deuterium come from? Well, it could come from D2, which is an isotope of H2. But H2 is not a electrophile. D2O, readily available. If you treat this with D2O, this is analogous to H2O, and KOD, which is analogous to KOH, it's the isotopes, deuterium isotopes of all that. What you can get is exhaustive deuteration. All your acidic hydrogens can be replaced with deuteriums. How does this happen? Well, your Your base takes an H, and one over there also, and you get the enolate carbanion. Which are resonance structure, which will look like an enolate. That's the major resonance structure. But remember, enolates react on carbon, so there's really no need to show that resonance structure unless you're asked to. What can this do? This nucleophile, what can it react with? Well, we've got D2O. We've also got, we make that plus what? HOD. I mean, there's where the H is now. Got this and this. Now this can react with something. What about this equilibrium? Which is favored? Is this an equilibrium? Yes, sure. It can go backwards. While we're here, which side is favored? Starting or the anion? pK of this is what? 20? What's the pK of the acid here? That's essentially water. It's 16. Which is favored? 16 or 20? 20? Okay. See, that's favored. But this establishes an equilibrium. It goes back and forth. At any given time, that's favored by 10 to the 4. Okay, it can come this way. How does it go back? This takes the H and go back. But hold on. There's only 1 mole of this. This is molar to molar. This is a huge excess. So is it more likely to take an H? I mean, look, these are all the same here. We've got 1 H and we've got 3 Ds. Is it more likely to take an H or a D? D. Especially from this molecule, which is an excess, we take a D, and when we take a D, we don't go back there, but we go to what? We have a D there and an H here. Well, guess what? You can just repeat the process. You got excess base, take another H off. But then when it puts one back on, since we flooded it with D2O, is more likely to put a D back on. This is deuterium exchange, but we have to have a base. Because that's not a nucleophile unless we deprotonate it. Where did we do deuterium exchange before? NMR, and we said that H's on oxygen or nitrogen do exchange with the D2O shape. You see, if you take an alcohol and react it with D2O, you don't need a base because this already has a lone pair, and we can just do this. This is in your notes. Go back to the NMR. This is all in your notes. But this is going to go backwards. When it goes backwards, does it lose an H or a D? Well, to go here, it has to lose an H. No, it has to lose a D. But it could also lose an H, and you would get the OD. Okay? Basically, it's the same thing here, except over there you don't need a base because you already have a lone pair to start with. Here you have to have a base to do the exchange. Because that's not a nucleophile until you deprotonate it and give it a lone pair. So, in the end, this is just like halogenation. You take an H off, you put a D on. Take an H off, put a D on. Do it exhaustively. How many can you put on? 3? Now, what if you want to take the D's off? You can flood it with proton water. It'll take a D off. And when it tries to put something on, if you got more H's, it'll put the H's back on. So you can take them back off. It's the same mechanism, except you just deal with H's instead of D's. Okay, so what is it good for? This is often used in mass spec studies. Because if you think you've got this compound, one thing you can do with it is you can exhaustively deuterate and then see what change in mass occurred. If you exhaustively deuterate this, you get this, what's the change in mass? Plus 3. Everybody know what deuterium is? What's the mass of deuterium? 2. Regular H is 1. So every time you put on the deuterium, you're adding 1 to the mass. If you put 3 on, you add 3 to the mass. You take this, rerun the mass spec, and you see how much your mass increased. Hopefully, you would see an increase in 3. That would help prove that that's your compound. For example, if this was your unknown compound, you could maybe do an iodoform test and hopefully get a precipitate because you got a methyl ketone. That would help confirm you got this. I mean, of course, there's a million other methyl ketones, but if you thought you had this and the iodoform was negative, that'd be bad, wouldn't it? This should give a positive iodoform. But you could also exhaustively deuterate, and when you run the mass spec, if you thought you had this, how much should your mass spec increase? 8. Should increase by 8? Someone? 8, 9? Can I get a 10? Well, the question is really this, guys. How many acidic H's are in the molecule? Because all the acidic H's will get deprotonated, and when you reprotonate them, you'll reprotonate them with D. How many acidic H's? 3 there, 2 there, 1 there next to that. What's that, 6? 2 there, 8. I see 8. Why'd you see 9?
I don't know, I missed that.
Okay, I see 8. You should exhaustively deuterate and get 8 deuteriums. When you run the mass spec, the mass should increase by 8. If the mass increases by 9, what does that tell you about your proposed structure? It seems wrong, unless something else is going on. What if this had an NH right here? Then it would be 9. Because not only would you exchange those, but you would also exchange this, just like an NMR. OHs and NHs are exchangeable without treating them with base. Right? We learned that with NMR? Okay. So what's it good for? Mass spec study. It's also for testing young organic students and knowing how many acidic H's are in a compound and stuff like that. Okay. Now we're moving to B. What have we done so far on this handout? We saw that the alpha carbon of a ketone, or actually ester or nitrile, is acidic. Slightly acidic, pK about 20, 25. We can do chemistry. We halogenated that position, either under acidic or basic conditions. Under acidic conditions, the enol is the active species. Under basic conditions, the enolate. With the halogenation, we saw the unique haloform reaction. It had an additional elimination and a precipitate. Then we did the analogous deuteration. Okay? So we put halogen on the alpha carbon, deuterium. What else can we put on the alpha carbon? We can also put alkyl groups on the alpha carbon. And alkyl meaning carbon. We can add another carbon to the alpha carbon. Alkylation. So that's what we're going to move into now. Now if we treat this with sodium hydroxide, we can make this. We've already said that this is actually favored in equilibrium because the pKa doesn't favor this. We've said that at least twice. But the amount that is formed, we can do chemistry here. We can halogenate. What if we throw in, instead of like bromine, and this attacking bromine and we brominating, what if we throw in something like CH3 iodine? Could this attack something here? Well, this is just good old SN2 now. I mean, that's really SN2, but now we have a carbon doing SN2. It looks more like traditional SN2. And that would give what? I mean, we would just methylate there. Plus sodium iodide, plus water. I mean, we could have did this reaction in organic 1 when we were doing SN2. I would have just had to explain that this is acidic enough that we can deprotonate. But now you have a nucleophile, and boom, SN2. Problem is, this reaction doesn't work when you have, and I love this word, carbon electrophiles. Carbon, I can't hardly say it. Carbon electrophiles. Isn't that what that is? That's a carbon that's electrophilic. Because at equilibrium, which one of these do you have more at equilibrium? This side. This is favored at equilibrium. Okay? Thus you have lots of hydroxide. The hydroxide will react here and you will get competing product. Okay? Competing product. That's the problem there. Now you may say, well, why is this not a problem when you do bromine? Well, that would take a long time to explain. So we're not going to get into all that. But with carbon electrophiles, it doesn't work out. To solve this problem, what you need is you need to completely make the carbanion, and you need to get rid of your base. To do that, we need a stronger base. And LDA is the stronger base. If you use LDA, it will completely form this. What is LDA? What is LDA? No? Is LDA not in the textbook? I thought it was in the textbook. Okay guys, you got to read ahead. You got to be prepared for lecture. Okay? I know it sounds like I'm chastising you, but it's really what you have to do to succeed as a student. I would hope that many of you would know what LDA was today when you come to class. Okay? LDA is lithium diisopropyl amide. And amide is a misnomer, but it's diisopropyl. It's an anion, and the cation is lithium. Lithium diisopropyl amide. Now, that's not an amide for us. An amide is a nitrogen on the carbonyl. It's unfortunate that nitrogen anions are called amides. It's a misnomer. Somebody messed up a long time ago and called both of them amides. Okay? But that's what A stands for. I would call it a nitrogen anion. But that's what the A is. Okay? Now this is just, which is the stronger base, that or hydroxide? This, because nitrogen doesn't like being minus as much. The pKa of this is about, do I have it listed? I don't think I have it listed. It's about 35. Now, of course, that's a pKa referring to the conjugate acid. What's the pKa of hydroxide? About 16. Stronger base, 35. Everybody know your pKa's and what the numbers mean, high, low? Okay. Stronger base. This takes the H, leaves that behind. What do you get? You get this plus that, and that's 35. That's what I told you here. Let's see which side's favored. What's the acid over here? The thing with the H. What's its pKa, Andy? Peter? pKa. Yes. It's on the very first page. Very first page at the top. What is pKa of alpha ketone? Go ahead. Actually 20. Let's speak of this. 35. Which is favored? 20 or 35? 35 by how much? 10 to 15. What is that? 100 gazillion. You see, that's favored. Let's see, when we use 16, that was not favored. This was favored. We have a stronger base, completely favored. When this is done, do you have any of this left? I mean, you've got 1 out of 10 to the 17. That's none. Okay? None of this is left. This is complete because we've got a stronger base. Now when you throw in your carbon electrophile, you can now do this and you can get your product. This is no longer present because the acid base was complete. This could still be a nucleophile, but it's not an anion like these were, so it's not as strong. Why is this also not going to attack readily? Sterically hindered. That's the purpose of the 2 big isopropyls. It's to keep it from, if it was thinking about attacking, those big wings keep it from attacking. That's another reason, okay? Sterically hindered strong base. So here we don't have anything competing. There's no anion. That species is sterically hindered. I mean, that is too. And this is how you have to do if you want to do alkylation. The alpha position. You have to use a stronger base, and the most common at this level is LDA. Now knowing that, predict the, I've already given you the product here. I gave you the product in the first one. You take the ester with LDA, what we're going to do? We're going to deprotonate. Which side? Either, it doesn't matter. Now we throw in this carbon with a leaving group. Carbon. I tell you why I smile every time I say carbon electrophile. Y'all remember Carmen Electra?
Yes.
Some of you do? Alright. So we throw this in, and we do this, and we make that bond, yeah? About 10 or 15 years ago when I first said carbon electrophile, something came up about carbon electrophile. I don't remember. Okay. Does that make sense? Just the reaction we just did, LDA, and then throw in your carbon electrophile. Show the product to the next one. And then the next one. We've got 3 or 4 to do here. How about you guys on my left? Well, let's do the next one together, and then we'll do left and right. What's the second one down? That should be pretty darn easy here, guys. But you do have to know what's going on with the the details, pKa's, LDA structure and stuff. We've got phenyl. Get that right there, yeah? I mean, LDA makes the anion completely, and then we alkylate with SN2. So we put in an ethyl there. What bond did we just make? We just made that bond, right? What's next? That's not a ketone, that's an ester. Does it have an acidic proton? Yes, also next. It's not as acidic as ketones, so it's pK of an ester. Five? That's quite acidic. That's a carboxylic acid. 25. Okay, we talked about why it's not as acidic as that. Okay, 25 LDA is 35, which is going to be favored, 25 or 35? 35. The LDA is still fully going to deprotonate it. LDA will fully deprotonate ketones, esters, and nitriles. These are 25. Okay? You guys on the left show the product of that one. You guys on the right show the product of this one. Take that bond right there. That's not aromatic. Those H's are acidic, 25. We showed on the first page. Make a carbanion. Carbanion attacks here, and so we end up with an ethyl there. And we just made that bond there. Note that LDA, because it's sterically hindered, will not add to the carbonyl and displace the leaving group. It will not add to the nitrile. LDA will only act as a base and abstract a proton. Now, I reckon you could force it to do that other stuff, but in general practice, it doesn't do the other stuff. It just acts as a base. It's a sterically hindered base. If you tried to use hydroxide to deprotonate here, first off, it wouldn't really deprotonate. Second off, it would add here and displace this and hydrolyze your ester. So what did we just do there? It's written beside B. We did alpha alkylation of ketones, esters, and nitriles. LDA, very important. Any questions about the chemistry here?
On the first example there, why wouldn't LDA strip like both sides of that? Like, why would
the first one?
Yeah, why would you end up with a product that has on both sides?
It didn't specify. We're not using excess.
But if it was excess, it would.
If it was excess, yeah.
Okay.
Yeah. I don't know how many anions you could form. It's hard, it's hard to form a dianion, trianion. Usually we're talking one equivalent here.
Okay.
Okay. Well, the problem with LDA is, it's not a big problem, but it is expensive. You cannot have any water around it, so your solvents have to be super dry. If there's any water around LDA, the LDA nitrogen will just take a proton from water and you'll get hydroxide. Expensive, had to be scrupulous, dry. Your glassware has to be plain dry. Solvents have to be distilled and very dry. Because of this, there's indirect ways that have been developed. Not just because of that, there's other reasons why. But let's look at indirect alkylation. In indirect methods, we can use weaker bases, hydroxide bases, or ethoxide, oxygen anions. These are much more convenient bases, especially at sort of the introductory lab level. The very sophisticated labs that have lots of money and can do all these things very easily, they're fine with LDA. But it takes money to work that sophisticated. A lot of reasons oxygen bases are just more convenient. Indirect. The first way we're going to look at is the acetoacetic ester synthesis. And that's what it eventually gives. But we don't memorize that. We just look back, yeah, it is a methyl ketone. And here's the sort of the overview. Acetoacetic ester. What is that? Well, this is an example. That right there is acetic acid. That's the ester of acetic acid. and it has an aceto group over there. Acetoacetic ester. Okay? That's kind of a big name for this. A more generic name is a beta-ketoester. Because that's an ester. Alpha, what's at the beta position? A ketone. And it's written somewhere, I'll write it again. It's a beta-ketoester. When you get to biochem, you'll see lots of beta-keto acids and beta-keto esters and stuff like that. Now, the first is to use this base. First question is, where's the most acidic proton here? We've got alpha 2 carbonyl here and here. Which one's going to be more acidic though? The ones in the middle. Why? This is pKa of about 20. This is pKa of about 10 to 12. Much more acidic. So the weaker base abstracts it, and we get this plus what? Ethanol. Ethanol is like water 16. That's 10 to 12. Which side's favored? 10 or 16? 16. See, this is favored. It will fully deprotonate essentially. Why is this more acidic? Because that's more stable. Why is that more stable? Resonance into not one carbonyl, resonance into 2 carbonyls. It's resonance stabilized by 2 withdrawing groups. That makes it more acidic. This is an example of this type of compound where you have 2 withdrawing groups with the CH2 in between. By the way, what do we call a CH2? It's not a methyl. What is a CH2? We said it before. I don't expect you to remember. I probably just said it in the past. Methylene. CH2 is a methylene. This methylene has got some acidity. We can do this. Now we throw in a carbon electrophile. Did I say that right? And we do our reaction, and what do we get? We get that there. The only difference than before is we're able to use an oxygen anion base. Why? Because that's more acidic. But this here is a beta-ketoester. What we can do with this guy is we can treat it with aqueous acid and heat. What's that going to do to this? That's an ester. What happens with esters when you treat them with aqueous acid? Hydrolyzed to the carboxylic acid. So this is going to first give the hydrolysis product. We'll finish up right here. We can name this. I'm not sure if it's named here or not. This is what? This is a beta-keto, not ester, but what? Beta-keto acid. Okay, we just hydrolyze the ester. That's test 3, right? Well, what are beta-keto acids prone to doing? You don't know, but here you're going to know. Beta-keto acids will decarboxylate. They will lose CO2. This H will end up here. We will show the mechanism. We'll talk about it next time. When it loses, that's CO2. When it loses CO2, and the H ends up here, what do you get? You get that. It's just drawing different zigzags. Okay? So we will look at this. When you get to biochem, please remember and know that beta-keto acids readily decarboxylate. We will look at the mechanism next time. In the end, what do? We made the same compound as on the previous page, but indirectly. Indirectly. Okay, we'll summarize this next time. Please read ahead.